the size of the universe.
Fascinating. You've admired it, of course, on many a starry night, and you've probably thought the stars look like diamonds scattered over a black velvet cloth by some immensely rich king. But are the stars really studded haphazardly on the vault of the heavens? Or are they not rather distributed in depth, in space? And supposing they were, would they be distributed at random, like raisins in a cake? Or is there perhaps an architecture in their arrangement? Wouldn't it be wonderful if there were indeed such an architecture?
My task tonight is to tell you quite a bit about the arrangement of our universe. The arrangements of the stars, of the galaxies, of the planets, of the sun, how they all are together in the universe, what their distances are, and how they are related to each other. This photograph that we have here is probably as good a one to start on as any, because on this photograph we see dots, and every dot is a star, and these star dots are, each of them represent suns. All of them suns, very much like our own sun. Some are fainter, some a little brighter, but all suns in their own right. These little places that we see here, these smudges, they are galaxies. They are large star systems, well beyond our own star system or our own Milky Way system. And these star systems themselves are at very great distances from us. We shall find that these can be observed to distances as far away as 2,000 million light years. A really very great distance into space. The stars are somewhat nearer by. But before we turn to the stars, let us turn first to the nearest neighbors that we have. Let us turn to our own solar system. The plan that I have to start out with our own solar system and gradually move out from the sun to the planets, from the planets out to the nearest stars, from the nearest stars in our own star system, our own Milky Way system, to the farthest regions and beyond. And I hope to give you an idea as to how these are arranged. Now, the first photograph that I have here is of a very familiar and basically not very interesting object, the moon. All of you have seen the moon. You know that it is a companion satellite to our own Earth. It is not very far away from our Earth. Its distance is only a little more than 200,000 miles, which means that at the speed of light, 186,000 miles a second, a light ray goes from the Earth to the moon in a little over 1 second. Many of you will probably remember how about 10 years ago, for the first time, a radar beam was bounced off the surface of the moon. That radar beam, signal sent from the Earth, went towards the moon, returned by the moon to the Earth, took a little over 2 seconds to complete the whole trip. What we say is the distance to the moon is about 2 light seconds, or a little over that. But now let us really come to the important body in our solar system, which is the sun itself. Here is a photograph of the sun with some of the familiar sunspots shown in 1 or 2 positions. The sun is a star. It happens to be to us the most interesting star because we happen to be very close to it, and our Earth is one of the planets around our own sun. The distance to the sun is 93 million miles. Now you might say, Here he gets busy and throws large figures around and tells us about distances that are so large that we cannot imagine them. Let us just try a moment to imagine what 93 million miles is like. Well, many of you must have had a car that has run 93,000 miles. My own car has gone at the present time more than 86,000, so I know just how far it is to go about 86,000 miles, and I can imagine very well how far 93,000 miles is. Well, if you imagine a parking lot with 1,000 parked old cars, all like mine more or less, these 1,000 cars will have traveled 1,000 times 93,000 miles, which would be 93 million miles. I hope that that will give you an idea that the distance is great, but not a distance that we cannot imagine. Now, if I continue to talk all the time in terms of distances in miles, the figures would become so large and so unwieldy that they wouldn't make sense. For that reason, we measure in astronomy our distances more in terms of the time that it takes for a light ray to cover a given distance. Light moving at a rate of 186,000 miles a second travels the distance, well, that is about 7 to 8 times around the Earth in 1 second, travels the distance to the moon in a little over 1 second. It takes 8 minutes to go to the sun. We say, therefore, that the distance to the sun, that 93 million miles, is a distance of 8 light minutes, since it will take a light ray 8 minutes to travel that particular distance. Now we ask, what other distances are there in the solar system? Let us look at one of the other objects in the system, and we turn to the biggest and best of all the planets that we have, the planet Jupiter. Many of you have probably seen Jupiter. You probably have seen the belted structure, which comes in a cold atmosphere of ammonia and of methane. These little black spots, by the way, are shadows thrown by the satellites of Jupiter on the surface of the atmosphere. This planet Jupiter is at a distance 5 times as great as the Earth from our sun. Therefore, 5 times 93 million miles is the distance from the planet Jupiter to our sun. In terms of light minutes, 5 times 8 is 40 minutes. It would take a light ray about 40 minutes to go from the Earth, from the sun to Jupiter. If we move out, there are other planets. For example, there is the famous planet Saturn with its beautiful ring structure. It's a little farther out. Let us not worry too much about the details of the figures. But we can say that the solar system, with all its planets, is contained roughly within a distance of about 40 of these astronomical units, 40 times 93 million miles distance from the sun. That system has some very distant outlying members. The comets are probably the ones that go farthest out. There you see a very fine example of one of these comets. The comets, they are the objects that go farthest out in our solar system, and therefore we go up to distances of about 50 times this 93 million miles. To complete this, let us look at a diagram that gives you some idea about how this arrangement really works. Here we'll see Neptune, one of the outer planets. Pluto lies beyond it. Neptune up here, Uranus down here. Then we move in from Uranus to the planet Saturn, to Jupiter, to Mars, and the Earth. This distance from the sun point here to there, the next one, that is about 93 million miles. At the speed of light, therefore, we can say that the dimensions of the solar system, cutting once across the entire system, are of the order of about, say, 10 light hours. In other words, if you were to start from the Earth and right after breakfast and go out and want to visit all the planets and do so at the speed of light, it would just take you a full, long day's work and you would be home in time for a late supper. In other words, the dimensions of our solar system are measured in terms of light hours. Let us just note a few of these things on the blackboard. The first one that I would like to record here is that the distance from the Earth to the sun is 93 million. That must mean we need 6 zeros with that. 93 million miles. That is equivalent to 8 light minutes. The second one, that's the dimensions of the solar system. So we go through the solar system from one end to the other in about, say, 12 light hours. So moving at the speed of light, 12 hours to go through the solar system. Well, that gives us our first basis for discussion. We know how far it is now from the Earth to the Sun, what the dimensions are of our solar system. And now we turn to the system of the stars. In this very fine photograph that I have here, you will see a section of our Milky Way. It happens to be the section of the northern cross of Cygnus. Those of you who know your stars may notice Deneb up here. Albireo, the end of the cross, is just off the photograph. Here we have the crossbar. In this photograph you see a great many dots. And you remember from the earlier one that every one of these dots is a star, that every star again is a sun, and that these sun stars are in many cases brighter than our own sun, in other cases intrinsically fainter. In other words, our sun is a pretty average sort of a star. When we ask about distances to the star dots here, they will come out something of the order, not of light minutes, but they're measured in terms of light years. Let me first of all remind you that whereas the dimension of the solar system is measured in terms of light hours, 12 we wrote on the blackboard, that the distance to the nearest star, so from our sun and the planetary system to the next star, is 4 light years. The first thing that we notice about the universe is that it is a very big and empty place. Here we are with our solar system, about 12 light hours. You got to travel at the speed of light for 4 years to reach the nearest star. When you take an average star dot here in this photograph, the distance of that star is not 4 light years, but more likely 4,000 light years. We see therefore that there is a terrific depth to the space that we have. Let us look at this photograph a little further. For from it you can begin to see some of the basic features of the structure of our Milky Way system. As we come from one corner of the photograph and move slowly closer and closer towards the center, we come to more and more star-rich regions. You will find that generally everywhere in the sky. If you look at the band of the Milky Way in the sky, that can be seen very beautifully at certain times of the year, then you will find that the band of the Milky Way is a region of high star concentration. There are more stars as you come from a distance and go towards the Milky Way in the Milky Way than at some distance away from it. In other words, it looks as though the Milky Way band is a real band of star concentration. We find that the stars in the Milky Way are at many different sort of distances. Some are nearer, some farther away. In other words, the Milky Way has great depth. Our sun is a star near the central plane of a large system of stars known as the Milky Way system. A highly flattened system. As we can see, go at right angles to it, very few stars. In the plane, many stars indeed. Here we have a section in the Milky Way. Let me draw attention to 2 other features. One of them, this little nebula, called the North American Nebula for obvious reasons. Here you can see almost the Panama Canal, the Gulf of Mexico, Cape Cod is missing, and here is the coast of California. Well, this nebula is made out of gas. It is gas that floats in between the stars. Because for every 3 grams that we have in the region around the sun in terms of all sorts of matter, 2 grams are squeezed in the stars in the sun. The other gram is left to float free as gas and cosmic dust in between the stars. This dust is shown, for example, here in the Gulf of Mexico, or the Pacific Ocean, or the Atlantic. Tiny little icicles that float in between the stars. Now let us have a good look at the Milky Way by itself. The next one shows you the outline of our Milky Way chart. Remember that we had this region up here in our photograph. We know already that these clouds are not really clouds, but they are really star dots, effects of a great many stars coming close together. In the Milky Way, we know that the concentration of stars increases as we go from the outside towards the central band. We notice something else. Some parts are exceedingly brilliant, like this one up here, near Scorpio and Sagittarius. Another part, the part that we see from our latitudes in winter, near here, Taurus and Orion, that part is very much thinner. What is the case? When we look at this photograph, we see here certain parts are very bright and brilliant, like this part that we see in the summer, Scorpio, Sagittarius. Other parts are very much weaker, like the part in Taurus, the Bull, and in Orion that we see in our winter Milky Way. Why is that? Simply because we are in the central plane of the system, but pretty far away from the center itself. Let us have a look at one more of these gas clouds of the Milky Way, because we shall find that they, the clouds like this up here, they really give a general outline of the structure of our system and especially delineate where the spiral features are in our system. The dots here, suns again, the gas shown as white, beautiful clouds, the little things like this little black hole here, the keyhole nebula we call this, they are produced by the cosmic dust. The Milky Way system, if you could see it from the outside, it would probably look something like this system up here. We were probably living in a point in this large star system like the one shown here by the black arrow. Our point is roughly about 27,000 light years away from the center. The diameter of the system approximately 100,000 light years. A few years ago, Mrs. Bock and I drew a diagram of our Milky Way system, and it still serves pretty well to show you what dimensions are involved. The only thing that we need to do today is, whereas a few years ago we thought this was a scale of 100,000 light years, it is now more likely that this represents 80,000 light years. But if you take that one correction, this gives a good picture. Looking down on the Milky Way, the sun here, the center of the Milky Way here, a distance of 27,000 light years. 100,000 light years roughly from one end to the other. Seen sidewise, there you have the general picture of our Milky Way system. One final point. The Milky Way moves around, rotates around the center. From here to there, 27,000 light years. We move with a speed of 140 miles per second. That means, while I say 1, 2, 3, the sun, the earth, and everything with it has gone 140 miles. How long does it take us to go once around, just one complete circuit? Well, the next graph will show it to you. You will see that it will take you quite a while to complete one circuit. 200 million years. So one galactic revolution takes place in 200 million years. We call that often one cosmic year. This will give you an idea of the tremendous size of our Milky Way system. So much for the Milky Way. Let us write a few of the facts on the blackboard. First of all, that the diameter of the Milky Way system, I write it as MW system, is about 100,000 light years. Let us write up the next thing. The distance, sun to center, is 27,000 light years. And the distance to the nearest star, distance sun to nearest star, is 4 light years. There we have sort of the facts of life as they affect the stars and as they affect the Milky Way system. And now in the final few minutes, let us get out into the universe of galaxies. Each galaxy is probably a spiral galaxy, just like our own system is, like the one that I've shown you already. To give you an idea of it, Let this be a typical Milky Way system. 100,000 light years from here to there, our sun 27,000 light years from the center. To give you an idea of the arrangement, let us just take these Milky Way systems and suppose that all of them had the same dimensions as our own. Some are in fact a little smaller, but that is beside the point. The important question to realize is that these systems are roughly about 1 million light years away, which in other words means this, that if we want to build up the universe, take a series of these disks, make each of them 100,000 light years across, put them 1 million light years apart, and then throw them out in space, like we're doing here. There they go. Be sure they stay 1 million light years apart. Keep it up for something of the order of about 2,000 million light years, 2,000 million light years, and you have the universe of galaxies. Now there is the universe. Let us have a look at it and see some of these things in a little more detail. Here is one of these galaxies, much like our own probably, spiral structure, gas, dust, all the various things in it, shown rather nicely in a photograph with the 200-inch telescope of Mount Palomar. We show you another one that we see edge on rather than face on. And there you can see, again, the central bulge that we had. Our sun would be in a position like this. This black belt in the middle is produced by the cosmic dust that shields off the light from the more remote objects. Let us look still at some others. Then we'll find out, for example, that one of the most famous of all is the famous Andromeda Galaxy. You can see it faintly in the sky as a faint star, sometimes with a little blur. When you see it in a photograph, you see the spiral structure coming out in it. You can actually photograph with the big telescopes the individual stars in a galaxy or Milky Way system of that sort. This one is probably in reality a little bit bigger than the one that we've had already. Let us look now at some that have a slightly different structure, like this one up here, where we come into one that is irregular in shape. This is a satellite galaxy to our own Milky Way system, the Large Magellanic Cloud. But you see there are the common components of gas, stars, and dust that are ever present. Well, let us finally say, how far can we go out? Here is one photograph of a really distant group. Here we're coming in terms of distances of 10 million, 30 million, 100 million light years and bigger. We're really moving out in space. Finally, when we come to the real distant ones, we will find that we come into distances that are still far greater. We find, for example, that there are some that recede from us with terrific speeds at very, very fast rates of the order of about, say, this one here, 20,000 kilometers per second. That is about 14,000 miles. Some have been measured with speeds 5 times as big. This distance has a distance of about 100 million light years. The greatest distances for which this expansion effect has been measured run as high as about 500 million light years. We go beyond that. The faintest galaxies that we can photograph are probably 2,000 million light years away. Well, in the last minute, let us return right to the blackboard and see where we are again. And here we have our picture. I'm starting now, we might almost say, from the bottom up. Remember that the galaxies measure about 100,000 light years across. Some a little smaller, some a little bigger. Let us remember, too, that the nearest star is even still 4 light years away from us. Remember that these galaxies at these dimensions are about 10 times as far apart as their diameters, that we go up to distances as great as 2,000 million light years. Remember, too, that in these light years, that light goes around the Earth 7 to 8 times in 1 second, 8 minutes to the sun, 12 hours through the solar system, 4 years the distance to the nearest star, 100,000 light years per galaxy, and there we have about the story of our universe as far as dimensions are concerned.
You saw some very beautiful photographs. They were not taken just for the sake of their beauty. They are one of the most effective means by which the astronomer gains precise information about the universe of stars. The astronomer makes measurements on these photographic plates, A 32nd of an inch on one of these plates corresponds to an angle much smaller than what a scientist could measure with the most accurately made mechanical device. Then, using these measurements, the astronomer finds, for example, the distance of the Earth from some of its nearest neighbors. The work of the astronomer has much in common with that of the other scientists. Each group of scientists has its own reasons, his own enthusiasms. The physicist has his own idea of the beauty of physics. And unfortunately, that is not a kind of beauty which is obvious to the non-physicist. On the contrary, the overpowering beauty of the things you've seen is just as apparent to you as to the astronomer. Another driving force, even more important to the astronomer than beauty, is the intellectual challenge of his work. He, like other scientists, has an intense curiosity about his field. Every understanding of it he obtains increases its beauty for him. The astronomer's work is a continual give and take between astronomy and the other sciences. He makes use of optics and mechanics in the design of his telescopes. Electronics is for him a basic tool. By means of chemistry, he finds out what elements exist in the stars. And in turn, while astronomy makes use of the latest advances in these sciences, it presents to them the most fascinating and rewarding problems. For instance, events at the surface and inside of stars takes place at such very high temperatures and pressures that we know almost nothing of the behavior of matter under such extreme conditions. The urge of understanding the why of certain astronomical appearances thus pushes the chemist and the physicist into regions of extremely high pressures and temperature combined, which he might not otherwise have felt compelled to investigate. In this give and take between the sciences, it seems to me that astronomy has given more than it has received. It has brought to light this all-important truth: nature is one. The laws of dynamics, the laws of physics and chemistry are the same, whether they work here on our Earth or thousands of millions of light years away from us in the depth of space. This, it seems to me, is one of the most important facts which has been impressed on us by the work of the astronomers.
This is National Educational Television.